The paper we are breaking down today is titled Eliminate Branches by Melding IR Instructions, or as it's known, MERIT. And it's a fascinating new way to think about one of the oldest enemies of high-performance computing.
It really gets to the heart of the branch misprediction problem. On modern processors, these unpredictable branches can cause catastrophic performance penalties. We're talking losses of up to 18% in IPC, or instruction per cycle.
And the usual software fix, something called if conversion, just doesn't really cut it on by86 architectures, right? It kind of falls flat.
It does, mostly because by86 is missing some key hardware support. Plus, it creates a ton of instruction overhead and runs into some really tricky memory safety issues.
This is where MERIT comes in with a totally new approach. It's a compiler transformation that, instead of just duplicating everything, strategically aligns and melds, that's the key word, only the similar operations at the intermediate representation level.
And that shift in strategy delivers some really impressive results. They implemented it as an LLVM pass, tested it on over 100 programs, and saw a geometric mean speedup of 10.9%.
Which is already great, but in some cases, for really tough code patterns, the speedup was just astonishing, up to 32 times faster. And it does all this while handling memory operations safely and keeping the code size down. So our goal today is to really unpack the how and why behind MERIT.
Yeah, to really get why a 10% speedup is a big deal or why 32x is even possible, you first have to understand just how much of a crisis branches are for a modern CPU.
Right.
Today's processors are these superscalar beasts, and they rely on something called speculative execution to keep their super deep instruction pipelines full all the time. It's how they get such high throughput.
And that's exactly where the problem starts.
Yeah.
When the CPU sees a conditional branch, like an if statement, it hits what's called a control flow hazard. It's a fork in the road.
Exactly. And the processor can't just stop and wait to see which way to go. It has to guess. It has to speculatively start fetching and executing instructions from one of those paths.
If it guesses right, everything's great. The pipeline stays full, performance is high.
But if that hardware branch predictor gets it wrong, well, the outcome is catastrophic. The processor has to immediately just throw away all the work it did down that wrong path. That's called a pipeline flush. Then it has to restart the whole process from the correct spot.
And since modern pipelines can be, 20 or more stages deep, that penalty means you're wasting dozens, sometimes hundreds, of cycles doing absolutely nothing but waiting.
Yes, and while the hardware predictors are amazingly good, they really, really struggle with what are called data-dependent branches. These are branches where the outcome depends on some runtime data that doesn't follow a nice, neat pattern.
So, okay, that brings us back to the software side. The traditional compiler trick for this has been if conversion.
Right, and the concept behind if conversion is actually quite elegant. The idea is to just eliminate the conditional jump entirely. You convert the control flow into data flow.
So you end up with one single straight line sequence of instructions that the CPU can just chew through.
That's the dream. But on an architecture like by86, that dream immediately hits a brick wall.
You mentioned the lack of hardware support. What's the specific feature that's missing?
Big one is native hardware predication. It's a feature you'd find on architectures like ARM, for instance. It lets an instruction run, but its result is only actually committed, written to a register or a memory, if a certain condition flag is true.
So it's like the instruction runs, but it's on mute until the CPU gives it the green light.
That's a great way to put it. If the flag is false, the instruction effectively becomes a no-op. It does nothing.
And without that on by86, if conversion has to do something much less efficient, it has to, just run both paths?
Exactly. It runs both paths speculatively and then uses a select operation at the end to pick the right result.
Okay, I can already see the safety problem there. What if one of those paths tries to, say, write to an invalid memory address?
You've hit on the showstopper. If one path contains a conditional memory operation like a load from a pointer that's only valid if you took the other path, then executing both is just fundamentally unsafe. You could trigger a crash.
So if conversion just has to give up, it has to skip over huge chunks of code that could otherwise be optimized just to be safe.
Yes, and even when it is safe, the overhead can be brutal. If your if and else blocks are large, duplicating all those instructions just to pick one result at the end, well, it can easily make your code bigger and slower. It completely defeats the purpose.
Precisely.
And that's why MERIT represents such a paradigm shift. It starts by operating at a different level. At the high level, target independent intermediate representation, or IR.
Which gives it, a bird's eye view of the code's meaning compared to just looking at machine instructions?
That's a good way to think about it. And from that vantage point, the authors had this key observation. Divergent paths, the if and the else, they often perform structurally similar operations, even if the actual data, the operands, are different.
So both paths might do an addition, or both might do a memory load, just with different numbers or different addresses.
Exactly. So Merritt's whole strategy flips from if conversions compute everything, select the result, to select the operands, compute once.
Ah, that's clever. So instead of doing 2 additions and picking a result, you pick the right inputs first, and then you only do 1 addition.
Yes. By merging those similar instructions into a single one with conditional operand selection, Merritt gains this huge efficiency.
Let's really dig into that efficiency game, because that's what tackles the overhead problem. The paper talks about reducing static instruction overhead. For someone not deep in compiler jargon, what does that actually mean?
Static instruction overhead is basically your code size. It's the number of instructions physically in your compiled program. If conversion takes path A and path B, duplicates them both, and then adds select instructions on top, the code size just balloons.
But Merritt avoids that by merging. So in the paper's example, if each path has 3 similar operations, if conversion might spit out like 9 total operations.
Right, whereas Merritt, because it only needs to insert selects for the inputs and then runs the actual operation just once, might only generate 6.
And that smaller code size has real-world benefits. Better instruction cache usage, fewer cache misses.
Yeah.
It all adds up.
It's a huge deal. It directly attacks the biggest weakness of older branch elimination techniques.
Okay, so what about the other big weakness, memory safety? That was the deal breaker for if conversion. How does Merritt get around it?
It uses that deep IR level semantic analysis. When it sees a conditional load or store, it actually transforms it into an unconditional load or store.
Wait, but isn't that unsafe?
It would be, but here's the clever part. It uses the original branch condition to select the correct memory address and the correct value to store before the instruction executes. So the memory operation itself always runs, but its inputs are guaranteed to be safe and correct based on the original logic.
Got it. So it moves the conditionality from the operation itself to the data that feeds the operation. Very smart.
And finally, the fact that it's target independent is a huge bonus. Because it creates this clean, branchless, select-based code early in the compilation pipeline, it makes life so much easier for all the optimizations that come later.
Right, things that are normally blocked by all those messy branches, like better instruction scheduling or vectorization.
Yeah.
They can suddenly work their magic.
Exactly. It just opens up a whole new set of optimization opportunities downstream. Now, to actually perform this melding, Merritt needs a really systematic way to find the best possible match between 2 different instruction sequences.
And this is where they did something I found really cool. They borrowed an algorithm from a completely different field.
They did. They adapted the Smith-Waterman algorithm, which is, funnily enough, famous in bioinformatics for aligning DNA sequences.
That's amazing. So instead of matching up genes, it's matching up machine instructions. How does it decide if 2 instructions are a match?
The paper defines what's called a compatible pair. That's basically 2 instructions that have the identical operation, say they're both an add for integer addition, even if their inputs, their operands, are completely different.
And the goal is to find a complete alignment, where every single instruction in one path is perfectly paired up with a compatible one in the other path, with no leftovers.
That's the ideal scenario, yes. But of course, real-world code is rarely that clean. You're often left with an unaligned instruction in one path that has no compatible partner in the other.
So you have a gap in your alignment. What does Merritt do then?
To fix that gap and get a complete alignment, Merritt has to insert a synthetic or dummy instruction. They call it an extraneous instruction. It's basically a placeholder that it puts into the opposite path to even things out.
Okay, but that brings back the safety question, especially with memory. If your unaligned instruction is a store and you insert a dummy store on the other path, you could be corrupting memory, right?
Absolutely, and they have a very careful solution for that. If the unaligned instruction is a memory operation, the extraneous instruction that it creates has to write to a special, compiler-allocated and initialized safe global memory space.
Sort of computational sandbox.
Pretty much. Through that semantic analysis, the compiler guarantees that this little patch of memory doesn't overlap, or alias, with any real memory location in the program. So the extraneous store happens, but it's basically writing to a black hole. It can't cause any harm.
So managing that safe global memory space, Does that add any overhead? Like, could it cause extra cache misses or something that slows things down?
That's the trade-off they have to manage. The overhead is usually just a single extra store instruction, and the cost of that one safe store is almost always insignificant compared to the cost of a pipeline flush that wastes hundreds of cycles.
So it only does the transformation if it's pretty sure it's a net win.
Right. It uses a scoring system. It looks at the number of matches versus the number of gaps that require these extraneous instructions, and it only proceeds if the predicted benefit is above a certain threshold.
And this whole mechanism, this is what enabled that incredible 32x speed up on the tuper function example, right? Why was that specific function such a perfect target for merit?
So tuper is a classic hard case. It's a loop that iterates over a string, and inside there's a conditional jump that checks if a character is a lowercase letter. If it is, it performs a conditional memory store to overwrite it with the uppercase version.
And that branch is completely unpredictable. It depends entirely on the input text.
Totally unpredictable, and traditional if conversion throws its hands up because of that conditional memory store. It's too unsafe. But merit steps in, uses the extraneous instruction trick to safely handle that store, and melds the paths together. It turns this chaotic, unpredictable bottleneck into a simple straight-line piece of code. That 32x result really shows how powerful this is for problems that other methods just can't touch. When merit is applied to these small, targeted micro benchmarks, the results are, well, they're undeniable. You get the 32x onto upper, an average 48% drop in mispredictions. It's fantastic. But when they scaled up to complex real-world applications, things gain a lot more complicated and a lot more counterintuitive.
Yeah, it looks like just turning on the standard back-end compiler optimizations, what they called Merito 2, sometimes actually made things worse. There was a 33% performance loss on one benchmark. How does turning on optimizations make code slower? That feels completely backwards.
It's a classic case of the left hand not knowing what the right hand is doing inside the compiler. Merit does its work very early on. Then, much later, these downstream optimization passes come in.
And they don't know anything about merit.
They're merit blind. They are trained to see traditional branchy code. When they encounter merit's unusual select-heavy branchless code, they sometimes decide it looks unoptimized and try to fix it by reintroducing branches.
So the compiler's literally undoing the very thing merit was trying to achieve.
In some cases, yes. It just highlights how delicate these complex compiler pipelines can be.
But the even bigger lesson came when they applied merit indiscriminately to massive benchmarks, like Specret or Squalite running database queries. Doing that actually led to an overall performance degradation.
And this is where profile-guided optimization, or PGO, becomes absolutely essential. The reason for the slowdown is that merit was wasting its effort transforming branches that were already highly predictable.
Ah, okay. So if the hardware is already guessing the right path 99.9% of the time, the tiny benefit of eliminating that branch is completely wiped out by the overhead of adding all the new select instructions.
Precisely. You're fixing a problem that doesn't exist. So the solution is merit PGO. You run the program once to collect profile data, find out which branches are actually unpredictable, and then you only apply merit to those specific problematic functions.
And once they did that, the results flipped completely. They started seeing positive speedups across the board. It proves this is a scalpel, not a sledgehammer.
And this targeted approach leads to probably the most fascinating result in the whole paper, what they call the IPC Paradox. In some cases, merit PGO caused a huge drop in instructions per cycle, IPC, as much as 26% lower, at the same time that the program's total runtime decreased.
Wait, hold on. The program runs faster, but it's executing fewer instructions per cycle. How is that even possible?
It sounds totally impossible, but it reveals a fascinating quirk in how we measure performance. Okay. So, remember the formula. IPC is the total number of instructions retired divided by the total number of cycles.
Okay, so for IPC to go down, either the number of instructions went way up or the number of cycles didn't drop enough.
It's actually the opposite. In the baseline case, without merit, when the CPU mispredicts a branch, it speculatively executes and retires a huge number of instructions down the wrong path. These instructions are ultimately thrown away, but they still count towards that instructions retired numerator.
Oh, I see. So the baseline IPC number is artificially inflated by counting all this useless, wasted work.
Exactly. Merit comes in and eliminates that entire stream of wasted, mispredicted instructions. Now, merit does add a few of its own extraneous instructions to the correct path, but the overall reduction in retired instructions is massive, so you end up with a much smaller numerator divided by a slightly smaller number of cycles.
And that new ratio is a lower IPC, even though The total time, the denominator, the thing we actually care about, has gone down.
That's the paradox. It shows that Merit's real power isn't just executing code faster. It's preventing the CPU from wasting enormous amounts of energy executing code that was never supposed to run in the first place.
So despite these really impressive results, the authors are very clear about the limitations, which I think is great. The first major hurdle they point out is the need for a better static cost model.
Right. The current model, which is just based on that alignment score, is a bit too simple, too coarse. It can't always predict accurately whether the transformation will actually be profitable.
What would a better model need to consider?
It would need to be much more sophisticated. It would have to look at the alignment score, yes, but also the static instruction overhead it's adding, and crucially, the data flow dependency depth of the new select-heavy code. Basically, it needs to predict how long that new chain of instructions will actually take to execute.
And that's super hard to do early in the compiler at the IR level because you don't have all the detailed timing information yet.
It's very difficult, and this is where the authors suggest a really forward-looking idea. Maybe we can use AI for this. They propose exploring large language models or specialized models like traced to create an AI-driven cost model that can learn to predict the misprediction penalties for any given branch.
So you could potentially get to a point where this becomes a zero-cost static optimization, no profiling needed. That's a fascinating idea.
It would be a game changer.
And the second limitation goes back to what we were just talking about,
Yeah.
that conflict with the back-end optimizers. They're still merit blind.
Right. It's a communication problem within the compiler itself. The backend passes see this weird-looking code and don't understand the intent behind it, so they can make poor decisions or even undo Merit's work.
So the future work there is about, passing notes through the compiler.
Basically, yes. Using LLVM's metadata system to attach hints or annotations to the code. These hints would tell later passes, hey, this code is branchless for a very important reason. Please preserve this structure. It's about making the entire compiler pipeline aware of these advanced transformations. So to kind of sum it all up, Merit has really successfully tackled one of the hardest optimization problems on by86, those data-dependent, fundamentally unpredictable branches. By moving the optimization to the IR level and using this clever idea of melding instructions, it overcomes the safety and overhead problems that plagued older techniques like if conversion.
And it delivers these really significant speedups, especially when you use profile-guided optimization to aim it at the right targets.
Exactly. It's a proven, powerful new tool in the compiler's toolbox.
For me, Merit really highlights this powerful shift away from just relying on hardware getting better and better at speculation, and more toward really sophisticated compiler-driven software optimizations. And it makes you think. Given that PGO is so critical for making this work on complex systems like databases, what other kinds of huge data center workloads out there are secretly bottlenecked by these unpredictable branches? And maybe the more interesting question is, how soon before these future AI-driven compilers can automate that whole discovery process, applying aggressive transformations like Merit without ever needing a human to run a time-consuming profiling step? That's a future where the software is smart enough to fix hardware bottlenecks before they even happen.